So let us begin a new topic now, in which the aim is to try to understand the mechanism of organic chemistry reactions. So there are different ways to classify reactions in organic chemistry. And the first one, which I have here now in this page, is actually in terms of this classification is in terms of the changes that happen in the molecular structure of substances that participate in the reaction. And of these, there are three very important types of reactions: the addition, the elimination, and the substitution reactions. These are not the only type of reactions that belong into this category of changes in the molecular structure, of course, of reactants. There are other types as well, like, for example, the combustion reactions belong to this category. But because we want to understand the mechanisms that are in play in organic chemistry, these are the three reactions that we need to understand in particular. The other types of reactions, like the combustion, do not really understand any, do not really require a particular understanding of the mechanism. They're more straightforward. So if we understand how the addition, elimination, and substitution reactions in organic chemistry take place, that will be great. So that is why I only have these three names. Now, the addition reactions is when we add two species together and we take, the result is one single product. Elimination reactions in general are reactions which we have one compound and it breaks into two compounds, but usually the one piece that breaks away is a small piece, could be a molecule of water or some hydrogen halide, for example, some small molecule that breaks away, and the result, of course, is a different compound and this small molecule that breaks away. In substitution reactions, again, is when, as you can see from this general equation, is when we have a reshuffling of some atoms or some groups, and the results, the resultant products are something different from the reactants. So we have the formation, in other words, of two different products. Now, what types of reactions are more common depends on the type of organic compounds that we have. And a very important classification of organic compounds is into saturated and unsaturated organic compounds. And I assume that you already know what unsaturated and saturated organic compounds are, because our aim is to go straight into the mechanism of these reactions. So saturated hydrocarbons are hydrocarbons that have, first of all, hydrocarbons are compounds that are only made of carbon and hydrogen and nothing else. If they are saturated, means that all the bonds that are involved in these hydrocarbons are all single bonds, okay? Which means every carbon is bonds with four other items, which can be another carbon or hydrogens. There is a variation of the saturated hydrocarbons, which we can call saturated heteroatom compounds. When we, like here, for example, look at this word, saturated, this term, saturated heteroatom, is it's actually a hydrocarbon, but one of the hydrogens could be something else. The hydrogen has been replaced by something else, another type of atom or another functional group. Like here in this example is one of the hydrogens has been replaced with this hydroxy group. So this is not now anymore a hydrocarbon because it has oxygen as well. So we call it saturated heteroatom. But remember, it's like a hydrocarbon with one hydrogen replaced with something else. Because these are important compounds as well. So if it says saturated, means that all the bonds involved are single bonds as well. So for example, this one, which is an ethanol, how would it be? Let's write it here. This ethanol, let's write it in this form so that we can see all the bonds. So this would be hydrogen and a hydrogen and a hydrogen and another hydrogen. We see this ethanol. All bonds involved are single bonds. This is a single bond, yeah. All right. So just because here, instead of hydrogen, we have a hydroxy group, this is called a saturated heteroatom. Unsaturated now is when there is a double bond involved somewhere. An unsaturated hydrocarbon, like this one, unsaturated hydrocarbon, here is an example of, this is a thene. Let's write it in this form. Oops. It's a double bond there between the carbons. So this would have some shape like that. Each carbon is linked to, is bonded to two hydrogens, and the two carbons have a double bond. Just because there is a double bond now, this is an unsaturated hydrocarbon. And it is a hydrocarbon because the only atoms involved are carbons and hydrogens and nothing else. If one of the hydrogens is replaced by something else, which is not hydrogen, then we can call it an unsaturated heteroatom. Like in this case, you see this oxygen. So what would it be? What would this compound be? Let's write it down in this form again with carbon and another carbon. This one has 3 hydrogens. And here, this is linked to an oxygen and into hydrogen. This is ethanol, which is saturated. This one, because you see this double bond here connecting the bond between carbon and oxygen, this is considered unsaturated because of the double bond. And this is actually a molecule of ethanol. It's an aldehyde. So you see, whenever we have a double bond, the compound is considered to be unsaturated. And because of this oxygen here, this is an unsaturated heteroatom. So, all right. So why do we make a fuss now about the saturated and unsaturated? Because depending on whether it is saturated or unsaturated, there are different chemical reactions that can take place that can involve these compounds. For example, the saturated ones, the saturated hydrocarbons and also the heterocarbons or saturated heteroatom compounds can undergo elimination and substitution reactions, but not addition reactions. Why not addition? Because they're saturated. Each carbon is connected, is bonded with 4 other items. There is no space for anything extra to be added, so they do not undergo addition reactions. But they can undergo elimination and substitution. So these ones are reactions that can we meet in saturated hydrocarbons or heteroatom compounds. Now, on the other hand, the unsaturated hydrocarbons or unsaturated heteroatom compounds again, can undergo addition, and they can also undergo substitution reactions very often, and sometimes, but very rarely, some elimination reactions, but primarily addition and substitution. So it matters whether you're saturated or unsaturated. So this will help us to begin with the types of reactions that that saturated and unsaturated species can undergo, okay? Because then we can talk about this type of reactions in general rather than referring to a species in particular. Now, another important aspect that we need to bear in mind as a background to understand the mechanisms is another classification of that concern the organic reactions is the reagent types. And reagents are substances that participate in chemical reactions. Okay, so the reactants, for example, we can call them reagents. And now these reagents can be classified into special categories, which this classification is important in organic chemistry. For example, one classification is in terms of their electronic character of their reagent. And we classify them in terms of electronic character as nucleophiles or electrophiles or radicals. We are going to talk about this, but let us group them first to see what we're talking about. So the reagents can be classified in terms of the electronic character. Nucleophiles means that these species are electron-rich somehow, which means they tend to be negatively charged or having a partial negative charge. And electrophiles are species which we can understand as electron poor, which means they might have a positive charge or a partial positive charge, in which case they want to accept electrons. And then another very important species is the radicals, the free radicals. We're going to meet them in some reactions, especially with saturated hydrocarbons. And we're going to talk about these radicals where we meet them in this reaction so that to make more sense. So anyway, these are the terms that we are going to need very often, and we need to understand what they are. And another group in this category of the reagent types is when we classify them in terms, it has to do with redox reaction and the acid-bases reaction, where we talk about which one is the oxidizing agent or where is the reducing agent, this type of classification, which concerns the oxidation and reduction reactions. But the truth is that this group here is not very much involved in the understanding of the mechanisms that we need in these organic reactions. So, all right. Maybe the next step is to talk a little bit more about these nucleophiles and the electrophiles so that we know what is happening when we talk about the mechanisms of the reactions. So nucleophiles, yeah, by convention, that's a nice point, but no. By convention, the terms nucleophiles and electrophiles are used when we talk about species which react with carbon atoms, and that is why we meet these a lot in organic chemistry. But if these species react with other atoms which are not carbon, then we are more familiar with these species as bases or acids. In this case, because we are talking about donors of electron pairs and acceptors of electron pairs, these are classifications that we understand as Lewis bases or Lewis acids. Well, this is a parenthesis, really. You don't have to, strictly speaking, you don't have to know that. But I thought it was quite interesting. So nucleophiles and electrophiles are not really new species that we are going to meet. It's just names that we use in organic chemistry because if these species react with carbon atoms. And some more here on electrophiles and nucleophiles. Electrophiles, the word electrophiles actually means friend of the electron. Because friends of the electrons means that these species are actually have a somehow positive or partially positive charge and attracted to electrons. That is why they're called friends of electrons. So these are actually can have a positive charge or a partial positive charge. That is why they are electrophiles. They attract, they like electrons, in other words. So these electrophiles react readily with electron-rich centers. Now, what are these electron-rich centers? For example, we're going to see that a double bond between two carbons is electron-rich. So it can be an electron-rich center. Like, so let's have this example here because it's an important example. Or another electron-rich center could be in a compound where some species that has a partial negative charge. We are going to see such things. So these type of things are electron-rich centers. And these electrophiles react readily with these types of this type of centers, these electron-rich centers. Remember, electrophiles, they love electrons because they have a positive charge or partial positive charge. The nucleophiles are the opposite, of course. Nucleophiles means friends of the nucleus because nuclei are positively charged things. Obviously, these nucleophiles are friends of positive species, which means they have they either have a negative charge or a partial negative charge. That is why they love positive species. They are friends of nuclei. So these nucleophiles react readily with electron-poor centers. And obviously, whatever is electron-poor, an electron-poor center is an electrophile. Similarly here, an electron-rich center is a nucleophile, isn't it? I mean, these two things are nucleophiles. All right. So nucleophiles react readily with electron-poor centers, but this will make a lot more sense if we see them in real examples. And now, how do we know? How do we decide which centers in a compound are electron-rich or electron-poor? So centers of high or poor electron density, that means electron-rich or electron-poor, are identified through in terms of the electronegativities of the atoms which are present. So if we know the electronegativities of the atoms, then we can decide which one is the electron poor or the electron rich center. So here, for example, look at this compound here. It's an organic compound with it's a bromomethane, isn't it? So it's a bromomethane. One of the hydrogens has been replaced with a bromine. There is a bromomethane. This is the same thing here. It's a saturated hydrocarbon. But now the bromine atom, we know it's very electronegative. So from those two here, between bromine and carbon, between those two, in other words, this will be will have a partial negative charge because the most electronegative, and this will have a partial positive charge. So in this case, I mean, the electronegativity can tell us which one is the electron-rich center, which will be here, the bromine atom, and this will be the electron poor, which will be the most positive, therefore has a partial positive charge, the carbon here. And so this will be the, obviously this will be the electrophile, and this will be the nucleophile part of the molecule, isn't it? So in this molecule of bromomethane, the carbon atom is electron poor and acts as the electrophile, and the bromine atom is electron rich and acts as the nucleophile. So this is the nucleophile, and this is the electrophile. I'm not writing the whole word. Okay, the electrophile and the nucleophile. Now, in this molecule here, we have a different molecule where instead of bromine, we have a lithium atom there linked, bonded to the carbon, to this methyl kind of group. So in this molecule, though, it's the opposite. The opposite happens. The lithium is less electronegative, and therefore this will be the positive center of the molecule, and this will have a partial negative charge, which is the opposite of the previous molecule. So it depends what atoms are involved for us to decide which one is more positive and which one is more negative. I don't think you'll see a molecule like that in your examples, but you're going to see very often a molecule like that with bromine. Bromine, it's very common. It's an atom linked to bonded with an alkyl group here. Very often we're going to meet it. But nevertheless, it's interesting to know that, I mean, the electronegativity of the different atoms involved help us to decide which one is the electron-rich center and the electron-poor, and which one is the electrophile and the nucleophile. So in this molecule now, the carbon atom is electron-rich, which means it acts as a nucleophile. And the lithium acts as an electrophile. Okay. And the pi bonds are regions of high electron density. Well, that is why the double bond actually is considered to be an electron-rich center, because we have a sigma in the pi bond. So the pi bonds are regions of high electron density. It's just, they tell us, in other words, that the double bonds are to be considered as what is the nucleophiles, because they are nucleophiles because they are electron rich. It's here. They behave as nucleophiles. All right. And now that we have this basic knowledge, we can start by looking at the reaction. And I'm thinking of starting from an addition reactions, which I think it's easier to understand their mechanism. And of course, we have 5 minutes anyway. If we do not, we can start and we can continue next week, because we need to do a couple of lessons, more than a couple of lessons, to understand the different mechanisms of the different reactions. All right. So let us see these addition reactions, and they are called electrophilic addition of alkenes, because remember, alkenes, we said saturated hydrocarbons do not undergo addition reactions because they are saturated. What else to add? We cannot add. But addition reactions are very important when it comes to alkenes, because they have a double bond, and of course in other hydrocarbons with a triple bond, but we'll concentrate on the double bonds, and the representative category is the alkenes. All right. So we can start with what can we add to alkenes? We can start with an easy alkene, like ethene, for example, like ethene. That would be an ethene molecule. And we could add hydrogen, or we could add a halide. When we see this X, it means any halide. It could be chlorine or bromine or iodine, whatever. So we can add hydrogen, we can add a halide, we can add a hydrogen halide, or we can add water and so on. So these are things that we can add to an alkene, and the result will be from unsaturated, it will become a saturated something, but it will not be hydrocarbon. Depends on what we react it with. If we react it with hydrogen, it will become a saturated hydrocarbon. If we add something else, it will become a saturated hetero something, some other compound. So let us start with, well, hydrogen is easy. Let's start with a hydrogen halide. For example, hydrogen bromide. Let's say that this reacts with hydrogen bromide. What would be the result? The result, let's write this in this form. Sorry. Well, here we have the hydrogens, we see the double bond. I like this representation because we see all the bonds, and it's easier to understand what's going on. Now, and we have now the hydrogen bromide. What happens here now? Plus the hydrogen bromide. Oh dear, 1158. Maybe we should continue next week. Yeah, all right. Yeah, maybe we should stop here because there is another session happening. And anyway, we will start with understanding the mechanism of the addition, and then we can go to substitution and followed by elimination. We're going to see several examples of each, as long as we remember about what is the electrophile and the nucleophile, and so that we understand what is happening. We are going to use these curly arrows now in this type of reactions, and we're going to see several examples of each. All right.